Welcome back to the Deep Dive. We've compiled the articles, the research papers, and all the notes, and we are diving deep into what is, well, maybe the most transformative AI breakthrough of the last few years. We're talking about the democratization of high-resolution image generation.
Yeah.
I mean, if you've spent any time online recently, you have definitely seen them. These hyper-realistic, sometimes just completely fantastical images being generated by AI.
Oh, absolutely.
We are talking true state-of-the-art results, and the engine behind, almost all of this visual magic is something called the diffusion model, or DM.
DMs are just phenomenal generative tools. The way they work is they gradually add noise to an image, and then they train a neural network to do the reverse, to denoise it back to a clean original.
Right.
They really define the state of the art in things like class conditional image synthesis, even super resolution.
The quality is it's undeniable. But the price tag, that's the problem.
That's the huge problem.
And our mission for this deep dive, which is really rooted in a foundational CVPR 2022 paper, is to find out how researchers basically solved this enormous computational crisis. The challenge was this. Diffusion models were spectacular, but they were also, prohibitively expensive to run and train.
Exactly. And when we say prohibitive, we mean that training just one of these powerful pixel-based DMs demands an almost, well, an unfathomable amount of resource.
Unfathomable how?
The sources cite examples ranging from 150 up to 1,000 V100 GPU days.
Wow.
And to put that in perspective for you, the V100 is an industry-standard, very high-end, specialized chip. We're talking about continuous use of hundreds of these for months.
And the problem isn't just the training, right? It's also the time it takes to actually generate the image once the training is done.
The inference, yeah.
The inference.
That's right. Inference is slow because DMs work sequentially, step by step, denoising the image. So generating just 50,000 samples, which you often need for proper evaluation and research, that could easily take 5 full days on a single very powerful A100 GPU. This immense computational drain in both training and sampling, that was the primary bottleneck.
And that's exactly why the introduction of latent diffusion models, or LDMs, is so important. The whole mission was to radically reduce that complexity for training and sampling without losing that incredible visual quality.
It's all about making this technology accessible to a wider community.
Okay, so let's unpack this. Before we can get to the solution, we have to understand why the standard pixel-based DMs were so inefficient to begin with.
Great.
Why does generating a detailed picture of, say, a tiny texture require such extreme hardware?
It really it boils down to their operational space. They
Yeah.
work directly in the high-dimensional RGB pixel space.
So every single pixel.
Every single one of those millions of red, green, and blue values has to be calculated and optimized. It's a huge task.
And what happens when a model like this starts to learn the distribution of image data? The researchers, they broke it down into 2 separate learning stages.
They did, and this is really critical. The first stage is what they call perceptual compression, and the second is semantic compression.
Let's break those down, maybe use an example.
Okay, sure. Think of a high-resolution digital image of, a golden retriever puppy sitting on a wooden floor.
Okay.
Most of the sheer data, most of the bits in that file are dedicated to capturing these tiny high-frequency details. This could be the subtle grain in the photo, the slight color variation in the puppy's fur, the little textures of the wood.
Right. Things my eye wouldn't even really notice consciously.
Exactly. That effort to capture every single one of those minute details, that's the job of perceptual compression. These details, they don't change the semantic meaning of the image at all. But because the DM is operating on the raw pixel data, it's forced to spend this immense computational capacity just modeling those high-frequency bits.
So you're saying the network, in trying to learn how to generate a puppy, is spending maybe 80% of its resources just optimizing the almost invisible micro variations in the fur.
That's a good way to put it. Details that don't change the fact that it is, unequivocally a puppy.
And that latter part, the actual puppiness of it, that's the semantic part.
Exactly. Identifying the puppy, its pose, the floor, all that stuff, that's semantic compression. That's the meaningful part. And traditional DMs, because they're stuck in pixel space, they spend way too much capacity on the perceptual noise.
Which leads to, well, superfluous computations and just incredibly expensive optimization.
Yes.
What's so fascinating here is how latent diffusion models just explicitly decouple that wasteful, resource-intensive step from the really important generative step.
That separation is the core innovation. They basically said, we'll handle the minor details once, separately, so the DM can focus only on the high-level semantic meaning.
And the LDM approach does this by splitting the learning process into two distinct phases.
Right. Phase 1 is this crucial pre-processing step.
So tell us about that first step, perceptual image compression.
Okay, so this involves training a universal component, an autoencoder. It has an encoder, E, and a decoder, $. And this autoencoder is trained just one time, completely separate from the diffusion process itself.
One time.
Just once. The encoder takes the original image, which we'll call $6, and it maps it to a much, much lower dimensional latent representation, which we'll call ZIA.
And the key here is that this latent space, this GEA-MO, still contains all the important stuff,
But
right?
crucially, yes. The autoencoder is trained specifically to make sure that when you run that latent code ZRS back through the decoder, the resulting image is still perceptually equivalent to the original.
So ZS has thrown out all the high-frequency, perceptually redundant details, but kept all the necessary structure and meaning.
You got it.
Okay, so we've effectively distilled the image down to its core information and permanently thrown away the computational clutter. Now, the DM doesn't have to look at all those pixels. What happens in phase 2?
Phase 2 is the actual generative modeling. The diffusion model itself, the LDM, is trained exclusively within this new compressed latent space.
The cell space.
The cell space. The network only has to learn the distribution of that compressed data, not the full massive pixel space.
And this is where they show some real genius in the architectural design. By making sure the latent representation still has the spatial structure of the image, the network can use the most efficient tools out there.
Precisely. They use a UNet backbone, which is built mainly from 2D convolutional layers. A UNet is kind of the gold standard for image-specific networks because convolutions are just extremely efficient at processing spatial information.
So by keeping the latent space spatial, they unlock all these efficiency gains. And this is a huge leap over previous attempts to do this, right? You mentioned older methods like VQGANNs or these autoregressive transformers. Why did those struggle where LDM succeeded?
Well, those older methods, they often needed really heavy compression to even make the task manageable.
And that hurt the quality.
It did. It led to a loss of quality in the final reconstruction. And on top of that, some methods try to represent the image as an arbitrary 1D sequence, so you lose the inherent 2D structure. LDMs. Because they preserve that structure and scale more gracefully, they don't need such heavy compression. And that ensures much more faithful, more detailed reconstructions when the final image is decoded.
Plus, you get that incredible flexibility benefit. If phase 1, the autoencoding, is universal, you don't have to retrain that massive compression step every single time.
That is a huge economic and technical win. You train that autoencoder once, and then you can reuse that foundation for dozens of different DM trainings, fine-tuning them for new tasks, or even using it for other things like single-image CLIP-guided synthesis. It drastically speeds up research.
Okay, here's where it gets really interesting for me. Measuring the savings. Did this whole architectural shift actually pay off in terms of speed and, measurable quality gains?
Oh, it did, overwhelmingly. The researchers compared their LDMs directly against a pixel-based DM, which they called LDM1.
Okay.
And across their tests, the latent diffusion models provided a speedup of at least 2.7 times in both training and sampling throughput compared to that slow pixel-based version.
So it's not just that the final result is high quality, but the progress during training is fundamentally faster.
Yes. If you look at the training progress of LDM1, that pixel-based model, it was just very slow. The LDMs, even with pretty mild compression, just pulled away so quickly.
Let's talk about that compression factor. They analyzed different downsampling factors, which they called $5, from 1 all the way up to 32. Where was the sweet spot?
They found that downsampling factors of F4 to 7, 17.6 struck the optimal balance between efficiency and image fidelity. If you went too small, like 500 4.1, you were right back in that pixel trap.
On too large.
If you went too large, like 500 to 3202, you just compressed too much meaningful data, and the quality really suffered.
You also mentioned this massive FID gap. For a lot of us, FID is just another acronym. So what is Frischette inception distance, and why is a huge drop of 38 points such a massive deal?
Okay, so FID is essentially the gold standard metric for evaluating the quality of generated images. It's a mathematical measure that compares the statistics of your generated image set against the statistics of a real image set, the training data.
So it's like measuring the distance from reality.
That's a perfect way to put it. A lower FID score is vastly, significantly better.
So a 38-point drop is huge.
It's a massive. So when their model using an optimal factor of 8, LDM8, got an FID score 38 points lower than the slow pixel-based LDM1 after the same number of training steps.
Yeah.
Well, it proves two things.
Okay.
First, the latent model isn't just faster, it's fundamentally generating images that are statistically closer to reality. And second, that compression didn't actually impair the final quality ceiling.
And this efficiency boost, it didn't come at the cost of being competitive. I mean, they were setting new records with this.
Absolutely. They reported a new state-of-the-art FID of 5.11 on Syllabay HQ for unconditional synthesis. And maybe even more importantly, when they compared them to traditional GAN-based methods, LDMs consistently improved on metrics like precision and recall.
Which confirms they capture the whole diversity of data, not just a small part of it.
Exactly, something that adversarial networks notoriously struggle with.
If we connect this to the bigger picture, the reason LDMs really revolutionized everything is that the researchers didn't just stop at making the DM faster. They turned it into this flexible tool that could take any kind of instruction text, layouts, other images, and produce high-resolution output.
And that's where the crucial architectural addition comes in, the cross-attention mechanism.
Okay.
The researchers augmented the LDM's UNet backbone with these dedicated cross-attention layers. This allows the model to flexibly process general conditioning inputs, let's call them editable, like a text prompt or a bounding box, and map that information right into the intermediate stages of the UNet.
So that cross-attention layer is sort of like the translator. It links the external idea, like a text prompt, to the image generation process that's happening quietly and efficiently in the latent space.
That is precisely its function. And
Yeah.
this capability allowed them to train these incredibly powerful conditional image generators. For text-to-image, for example, they trained a massive 1.45 billion parameter model on the LAION 400M dataset.
And we saw the results of that. I mean, this is what led to the explosion of tools we have today. The paper shows the model generalizing so well to these complex user-defined prompts.
Yeah, generating intricate scenes, complex compositions, like photorealistic paintings of specific animals in specific places. Quantitatively, it just blew away the powerful autoregressive and GAN-based methods on tough data sets like MS COISO.
And it wasn't just text. They also excelled at image-to-image tasks.
They did.
For instance, super resolution, where you take a low-res image and make it sharp and high-res.
Right. Their model, LDM-SR, was extremely efficient while getting competitive performance. It actually outperformed the prior state-of-the-art model SR3 in FID metrics.
Wow.
And what's more, its output was actually preferred by human subjects in blind user studies.
Which brings us to one of the most exciting capabilities.
Yeah.
Massive high-resolution generation. We started this deep dive talking about the huge cost of high-res images. How do LDMs create these huge, consistent, megapixel images without, blowing up the training budget?
This is the real computational cheat code. And it's thanks entirely to the LDM design working in that latent space with that convolutional UNet.
How does it work?
For tasks that are spatially conditioned, like semantic synthesis or in-painting, the LDM only needs to be trained on standard, smaller images, like 256 by 256.
Okay.
But then, because the underlying mechanism is convolutional, it can be applied to a much larger latent space. It's like zooming out the canvas. It generalizes via convolutional application to synthesize these huge, consistent images in the megapixel regime, like a 512 by 1024 landscape, even though it never saw an image or that big during training.
Wait, hold on. So they didn't have to train the model on petabytes of megapixel images to generate megapixel images.
Yeah.
They just leveraged the convolutional nature of the network to extrapolate from small image training. That truly, truly democratizes the ability to create high-end visual content.
Precisely. And finally, this efficiency also showed up in complex editing tasks like in-painting. LDMs achieved new state-of-the-art FID scores there to seamlessly filling in large masked regions or removing objects from images.
So what does this all mean? I mean, this latent diffusion model paper is truly a landmark. It feels like it solved the resource scarcity problem that was plaguing generative AI.
It means that LDMs successfully provided a simple, elegant, and really efficient method to significantly boost both training and sampling efficiency of diffusion models. They decoupled the system.
Right.
They allowed the most expensive part, the DM, to work only in the most efficient space, the latent space. By getting the DM out of the computationally hostile pixel space, they maintained or even exceeded quality while making high-res image synthesis accessible to a much broader community.
It's a huge shift in the ecosystem.
Yeah.
And you reminded us at the start that the researchers made their pre-trained LDM and their autoencoding models publicly available.
And this raises an important question for you to consider. If that first stage, that universal auto-encoding layer that establishes the reusable latent space, if it only needs to be trained once,
Yeah.
what entirely new applications or downstream tasks beyond image generation itself could be rapidly explored and built on top of this efficient, foundational, compressed space? Think about the dramatic economic and environmental impact of sharing a highly optimized core layer like this across the entire AI ecosystem. We are really only just beginning to see what this shared foundation enables.